We should begin today's class. I realized that I didn't stick to my PowerPoint a lot, so today I'm gonna correct myself. We're gonna cover some PowerPoint slides. Then we can discuss something new, okay? Sounds good, everybody? So, because this is a lecture note, and many years from now, you might still look at it. And so any question on this slide? We talked about, this is the length of interest. So basically explain degree of optimization and n value, capital N. So this is, I don't think there's anything you guys should be confused of. So if you get the molecular weight divided by repeating units, you guys can get degree of optimization. Length of fully extended chain, in this case, it shows example when you have a bond angle is fixed, what would be the length for each segment, okay? Then you can use repeat. If it's 180 degrees, so you're gonna have a perfect straight line. C here is just define the angle between this dashed line, nothing fancy. So if you know the A and you know the angle, you can calculate C. If it's 180, that's just happen to be a perfect straight line, so it will be C will be twice of the length. If you the angle, your C gonna be smaller, and you can calculate fully extended chain for 10,000 monomer. I'm sure everybody knows this. You can probably calculate even in your dream, right? Nothing hard at all. So this is an example. If we have a fixed angle, what would be the bond length? If we ask you what's the contour length of polyethylene chain with a molecular weight of 28,000. Oh, you got it?
Yes.
Okay. So if you have molecular weight of 280,000, you can first calculate the n degree of polymerization. You can use the molecular weight divided by monomer molecular weight. This is 2.8 thousand divided by 28. So we know there's a degree of polymerization would be 10,000, right? So we can calculate. In this case, its bond angle is fixed. We can calculate bond contour length 2 times n. Remember, 2 where it came from is because we have two carbon bond repeating unit. Times sine theta divided by 2 will give you the contour length. And where is sine theta divided by 2 came from? This might be confusing to some of you. So remember we have bond angle. So this, let's call it AC. So this would be carbon bond. This is just the length of C. This is another carbon. So everybody has learned geometry in math class, right? If we draw a perpendicular dashed line, so what is the relationship between A and C if I tell you this angle is theta? So first, you don't want to look at this giant triangle. You just want to look at this half triangle, which I highlighted for you guys, right? So what is the relationship? This should be perfect symmetric. So in my green one, this theta should be half of that, because the other half comes here. When they add together, it will be the theta angle. Makes sense, right? All right. So now everybody familiar with the definition of sine theta, cosine theta, and tan theta? All right, I'm gonna have Sarah. You seem very excited. Tell me. Yes.
Sine is opposite over hypotenuse. Is that what you're asking for?
Yeah. So it will be in this. What will be the value? Let's call it A, and this is not gonna be C. C defines this. So this will be half C, and let's call this vertical line B. So what would be the sine theta?
AC over 2. Is that right?
No, it should be half C over A, because sine theta is.
Oh, that's right.
Going this way, where the angle is directly pointing divided by the longest line. Okay, so.
I think it's sine half theta.
Oh, yeah. Good call. So everything will be sine half theta. So in this case, then cosine half theta will be b divided by a. So in our case, we are calculating the longest bond. You can see we know the a, we know this theta angle. So this contour length will be coming along this line. This should be a sine half theta multiplied by 2. Right? So after class, play a little bit with the number. Make sure you can get this right. There is 99.9% chance it will be in the final exam. Can I be more direct? Okay. You guys all heard of that. And now estimate the size of a chain in spherical conformation. So what this spherical conformation example asks you to understand a little bit. What if the chain is throwing a bad solvent? Okay, if you're in a bad solvent, so in a good solvent, the chain will swell and will be swimming around like a newborn baby, like really happy and swimming. If it's in a bad solvent, it's not happy, so it will compact into a very tiny compact sphere. All right, so now how can we get the size of that? We can, if we know the density of material, we can use a simple way to calculate because we know how heavy each single chain is, and we know the density, we can get the volume. Because the mass is equals to density times volume, right? Times volume. So if we know the mass, we can calculate the mass. We assume a density, which is 1.11 grams per cubic centimeter. So that's just the density of the plastic. Most of plastic is around that density. Actually slightly lower because water has a density about 1, so this is slightly higher. So how do we get it? How do we get it? A weight of a single chain. A single chain.
You just calculate it from the molecular weight of the chain?
Yes, how? I know the molecular weight. Polyethylene should be, let's use this example, should be 28 grams per mole.
You multiply that by the number of units in a mole, that number that's like 10 to the 20 something.
Yeah, great answer. I like that a lot. So everybody understand what the definition of mole? I mean, some of you may not know. 1 mole is basically a quantity. And how big is 1 mole? It's huge. It's 1 mole is a counting unit. It basically says it has 6.10 to the power of 23. And anybody has some idea? 10 to the 6 will be milling. 10 to the 9th will be billion. 10 to the 12th will be trillion. So it's almost close to 1 trillion molecule. I wish I had that rich. But each molecule is tiny. That's why they don't weigh a lot. So we need 1 trillion molecular to weight 280,000 grams per mole. That means if you have 1 mole of molecular, it will weight 28,000 grams. So you can use this to calculate how heavy is each individual polymer chain. You can just use total mass divided by a number of moleculars in that mass. So this would be a mass of single chain will be 28 grams per mole, then divide by 6.0 10 to the power of 23. Okay, so this is how many molecules. So it's a lot. If you calculate it, you can get the mass, and then you can use volume to calculate the size. Because volume is equals to a spherical volume, 1 second, 3/4 of pi to the r cubic is the size of the volume, okay? So Joseph, question.
So if you're trying to cancel out the moles and end up with cubic centimeters, why
Yeah.
is Avogadro's number in the denominator in that equation?
Because this will be, let me think. 1 divided by, good question. I haven't thought hard of, so this must be, because this tells you grams per mole, right?
Right.
That is clear.
And you,
So we need to get cubic centimeters, so it should be the mole.
okay.
But let me look it up. What's the unit for Na? It must be unit will be 1 over the mole. Otherwise, it doesn't make sense, right? But this calculation should be right. This will give you what the size for each individual molecule. So each individual molecule, if it's fully compact, is very tiny. 4.5 times to minus 19 cubic centimeter. So if we assume it's compact sphere, we get the volume from a sphere because volume of a sphere is calculated 3/4 4/3 pi times r cubic. R is the radius of a ball. Okay, so if you know the volume, you can calculate how big is your polymer if it's really compact. So that will give you the size of the polymer chain from fully stretched. We talked about fully stretched. Amy, I'll get to you in just a second. Fully stretched is micron size, right? Then we talk about fully dissolved. If it's dissolving a Gaussian coil, it should be on the order of tens of nanometer. And you can squeeze all these chains if it's in bad solvent. Going from good one to bad one, it's going to collapse. So your coil will collapse to a globular. And it's a dense material. There's no voids in between it. If it's fully collapsed, it will go down to 4.7 nanometer. So give you some size idea how big the polymer can go from conformation change. Going from, let me do a demo. I like demo. So fully extended, when we fully pull it, there will be micron size, and it will, if you dissolve in solution, it will form a random coil. And there's a lot of voids in between them, all these chains. And this happens a lot of time when you polymerize in a good solvents or a SATA solvent. We will talk about those much later. But imagine it's just reasonable solvent, you can dissolve it. It will be like this. So another chain can actually go through here and they will entangle if it's concentrated enough. But if you put something like polystyrene in water, we know polystyrene don't dissolve in water. It will, I'm trying my best. It will be literally no void. That's what it makes this compact of this size, okay? So a polymer chain can go through several orders of size difference. Then we start talk about ideal chain. I think this we already, Amy?
I had a question about the previous slide.
Sure.
The number that you get at the very bottom, 4.7, is that like, what R are you using?
R is radius.
No, I know.
Basically half
How
of the
did you get that radius?
from the volume. So we know the volume. We can calculate R because volume is we just did.
Okay, so 4.7 is the radius.
Yes. So if you use if you know the radius, if you know the volume, you can calculate radius because this is only unknown factor. Pi is a constant. This is a constant as well. So you just need 3 times v divided by 4 and divide by v, then take a
Okay, I
root
was just
square.
unclear as to what 4.7 is.
So
I
that's the
get it
same.
now, just like it didn't have an equal sign or anything, so it's
Right.
it is.
Right. So that's just to tell you R. We can calculate that way. Okay, now this we already talked about. Several ideal chain model. So chains has no long range motion in this case. Ideal chain just means it's idealized. It doesn't exist in real world. So one of the major differences, you don't have something going to fold back to itself. So no long-range interaction. Then we derived 3 different models: free rotated chain, hindered rotation chain, and free joint chain. So we start with most of the simple one. So we're going to see the freely joined chain just in a second. This is an example when we talk about freely joined chain. Okay, right? Everybody familiar?
Can you go back to the previous slide?
Sure.
Okay, so the highlighted red portions in ideal chain are not happening. Like there's
Right,
Okay.
right. So that's what the major difference between ideal and non-ideal is. Ideal chain can fold back on itself. It don't see the interaction. There's no interaction, and it just don't forget about what happened last night. It just always had hangover. This joke is really good. I need to use it again next year. All right. So see. But in real chain, it doesn't. So it always has repulsive interaction. So your chain cannot come here because they say, hey, this is my room. Get off my campground. Go find another one. So you need to go this way. So actually, the size of polymer coil will expand when we calculate in real chain versus the ideal chain. Okay? So we talked about definition of different bond angles, bond lengths. And in the most simplest case, we talk about the bond is always the same length, L. And the simplest model is this bond angle theta is random, so we consider the freely joined chain model. Right? Everybody remember that. Then we start to talk a little bit about if there's a bond is fixed. Last class, we discussed about freely rotation model. So you can rotate around, but you can't bend back and forth. Okay, so you can rotate around. That's more realistic because a lot of polymer has a fixed bond angle. Polyethylene has 109 degree in the theta, and there was some interchangeable use in theta and gamma, so just pay a little bit attention to that. Oh, there's another good news for you guys. You want to hear about it?
yeah.
How many of you want to memorize all the equations? You can raise your hand. 0. Oh, great. My expectation matched you guys' expectation. So there always will be equation sheet. You don't need to you don't need to memorize it in the exam. So it will be provided, and all the equations we're going to talk about will be put there. So you don't need to worry about confusion from the angle, theta stuff. Okay? You guys will see it in the exam. And I'll show you guys the exam sheet before the exam so you guys have some idea what it will be on there. Then, not much to discuss. It's just a pretty simple model, help everybody to visualize how the chain behave in 3-dimensional. All right. So I kind of skipped everything about random walk because I thought it's really stupid to talk about random walk. A lot of professors like to talk about random walk to help everybody understand what happens in 3-dimensional. So I'll talk a little bit about that. So random walk is just a way for everybody to understand what the chain behaves. Because some people just don't like to imagine what is 3-dimensional polymer coil would behave like. So simplest way to think about a polymer chain, what it will behave is have 3-dimensional or even 2-dimensional walking on the polymer chain. So how does it work? How does it work out? Is imagine this is you. You're playing a kind of pretty dumb game. Somebody draw the grid, then ask you to throw a dice. The dice has 4 faces: forward, backward, left, and right. So you throw it, then you're gonna, according to what dice says, is if forward, you need to go forward, if left. So, because each time the dice, how it lands is really random. It just, if you throw the dice, it landed 10 times go forward, buy a lottery now. Because it's hard, right? Because the chance is that you have a quarter times quarter, you need time itself. So it's probably 1 out of 1,000,000 times you can land at 10 straight. So the more common one would be random, like this cases. And this resembles freely joined chain, because freely joined chain is saying, you think about, you have a bond is freely moving in this is 2D space, but in 3D space is similar. Okay, how this would be useful is, it basically helps you to understand your polymer end-to-end distance is basically related to how far you worked away from where you start. So this is an example if we do a this is what? This should be 1D. 1D random walk, because it's straight line. So what is 1D random walk? So it's going to be even simpler. You have a coin, you flip it, if it's head or tail. So head, you just move forward. If it's tail, then you move backward. All right, now I'm looking. So Zoe, can you throw this on your desk? Then I'm going to be the random walk guy. So do you want me to go forward? Is that forward or that's back? Forward. Okay, all right. Don't let me jump off the cliff. Throw it again. All right. No. Let's have a Megan throw it. What? All right, I'm 2 steps away. Jamie. Oh! All right, you can throw it one more time, then we are done. All right, but now I'm moving backward. So if you do this again and again, this is an example where you can go forward or backward. So this is the case if you first time throw, go forward, then backward. So this would be the random walk. So if you do computation simulation, I think Boran said she might want to help everybody to do a small coding to help everybody understand the random walk. So this would be, if you pick a random case, so this plot where the position of Dr. Gu at, it always starts from 0, right? Then depends on how many times you throw the eraser, it can be from 0 to 100. So if I keep throwing, like what we did in the class, a lot of heads, I will keep going. But then it should be random, right? So the point is, if you throw 100 times, it's will not likely to be 100 times straight. So you will not end up at the position 100. So for example, this is we start from position 0. If every time you throw it positively, so it should be a straight line. So throw 100 times, I will end up position not 50, but 100. But you can see this is a realistic case. There's a chance you can go back to where you are. There's also opportunities you can end up the value of 20, 25-ish. And why we want to talk about this? Because this mimics a freely joined chain. So if a chain is going back and forth in 3-dimensional space, this is pretty much like this case. We're going to end it up somewhere. In this case, the step size is 1, means every time I take a step of 1. But if we increase the step each time we jump 2 in the position number, we can see we potentially could have ended up somewhere further away where we start from. So if you now imagine the position is end-to-end distance, right? Where you start to where you end. The number of steps is bond length, number of bonds. So this is similar. If we have number of bonds goes up, it will deviate from where we center. If we take average, that will be average end-to-end distance. Does that make sense, everybody? Joseph? Yeah?
If you average all of them, which they all average to 0?
The absolute value will be 0. So that's why you need to take the absolute of positive and negative. So n square, then take a root square. You will not be 0. But you just take the position, it will be 0.
Okay.
Because the chance of you go forward and backward is exactly the same.
Right.
Okay, so this is some statistic. If you run times, we can plot a frequency or histograms. For each game, you can end up a position. So for example, if we do 20 games, So it will have distribution. You can see there's a good chance it's possible you ended where you start from, but there's also possibility you will be ended up, if you move 100 steps, you end up 25. So it's pretty much follows something called a Gaussian distribution, which means you have highest chance because you go forward, backward the same. So there you had the highest chance you basically end up where you start off. Then it will taper off at longer distance away from there. Okay? So, all right. So this is the fun part. End-to-end distance. So if we go back, this one, we count end-to-end distance from 0, because this will be end-to-end distance of 0. Positive 30 and minus 30 will be basically same distance where we start from. So if we plot that, you can see there's end-to-end distance distribution, very similar. Okay. This I'm gonna totally skip. So polymer is basically a 3-dimensional random walk. This is a lot of people like to teach random walk at the beginning of lecture, because if you think about what we did in the 1D, you expand 2D. This would be a random walk from 2D. And this would be 3-dimensional if you can go up and down, left and right. And this pretty much resembles a free joint chain. Not totally, right? If you fix angle, it should be freely rotation chain with a bond angle of 90, then it will be exactly like that. Does that make sense? So this would be a polymer with behavior. And so all these words is basically explain some of the backgrounds in the random walk. So for a truly random walk, there should be no correlation between each step. It sounds a little bit intuitive, because I fell into the trap that saying next step should be correlated with last step. And there's a lot of debating. So have everybody see what is a Russian roulette is?
Yeah.
All right, now this is going to be the most debatable part for the whole semester. How many you guys think next row is somehow related to the last one? Let's say if we walk to a casino, the previous dealer rolled 10 times red. Will the next time be green? The chances of green be higher. How many of you think that will be higher? You know? Now, when I was very young, I think, yeah, it must be equal opportunity. If you have more yellow, more red, you must have more green. So totally unrelated, okay? Each time when it's rows is totally independent, and that's pretty much like this case. Each time when you walk, it doesn't matter where the last time, even if it's walk 10 times straight, the next walk can be continued to be straight, equal chance to be left, right, up and down. That would be strictly freely random walk. Okay, so then we went to the tough part, talk about vector and scalar in our class. I think I explained everybody what is vector and scalar. So by now, everybody should know that vector has directionality built into it. So if you have a vector, make sure you understand it is a distance plus a direction. So, and we can use simple vector additions, vector multiplications to add things together. And one of the beauty of vector is we can just add each bond vectors, we can get end-to-end distance vector. That's like most simple math you could have. So that's why we can use a vector concept to use each bond, R1, R2, everything. When we add together, we can get end-to-end distance bond. And we use this simple tricks to get what the end-to-end distance value using the end-to-end distance square average, not the end-to-end distance average, because that will be 0. So in the next slides, in the past few lecture, we talk about we need to use dot product to use R to dot product itself, so that you can get end-to-end distance square. And in this case, we further simplify it to be a self-term. You know, if you have a bond dot product itself, we pull them out, separate them with vector dot product not with itself. Okay, in this case, you can get cross term. And we all know that the second half, the cross term will be 0, so that we ended up just a end-to-end distance RE square average will be n number of bonds times bond length square. Okay, so that was probably one of the most important findings in the first half of the lecture, right? And look at this writing. It says the end-to-end distance is proportional to n power of half and r power of 1, which means your end-to-end distance, if you need to increase end-to-end distance, number of bonds need to be not double but quadruple. If you want, or you can just simply increase the bond length twice of the length. Okay? So this was freely joined chain or random walk. Then we talked about last lecture going from freely joined one to freely rotation one. Amy, yeah?
So R and this is bond length?
Yes.
Okay.
Yeah, that's bond length. Yeah, I don't know why in the lecture I have to put an R, but that's a bond length. Okay, so we start to talk about end-to-end distance. We start to introduce the new model of freely rotation chain. So when in this case, your bond angle is fixed. Okay? Okay, so here is an example. In freely joined chain, we said theta and phi is really random. It can be any value between 0 and 180. Theta don't need to be 160 because when theta angle is above 180, it's symmetric. So you can think 150 is the same as 210 degree for the theta angle, right? So, but the phi angle need to go rotate from 0 to 180. So that's basically, it's a repeat what we said about end-to-end distance depends on number of bonds and bond lengths. It's the same. Here to give you some example why freely joined chain is beautiful in math. It's very simple. It's probably the simplest you can have. But it's highly unrealistic because it's so idealized. It has been experimentally applied to long polymer chain under several conditions. It needs to be very long. When n is small, it's sometimes there's this scaling relationship doesn't fully follow. And when the n is long, it defines that n is probably need to be bigger than 100, so 100 repeating unit. Or when your molecular weight is higher than 1,000 kilodalton, if it's really small, then it's not useful. It needs to be a Gaussian chain. Gaussian chain is another name for freely joined chain. And this is the most important part. No excluded volume. Exclusion is always a bad name, right? We want to be inclusive. But here, no excluded volume is basically says when the polymer is not feeling itself, it's not excluding the same part from itself. So what would be the special conditions? So turns out there are two very special conditions matches. It's a freely joined chain. So we're going to talk about those two conditions. One is, to everybody's surprise, Amy, you can ask question first. Yes.
What does Gaussian chains mean?
Gaussian chain is basically when the chain follows a Gaussian distribution. It's just another fancy name of freely joined chain or ideal chain. So they're used interchangeably. Ideal chain, free joined chain, Gaussian chain.
Okay, but like when in real life will a chain be a Gaussian chain? It won't?
It will be in those two conditions.
Okay.
So that's what in real life, you can see the free joined chain model can apply to polymer if you have two special cases. And case one, I would never imagine it. Case one would be if your polymer is not dissolved in a solution. So we talked about when it's dissolved, the polymer chain will fill each other and expand. So your end-to-end distance will be bigger than freely joined chain. But if you dry out the solvent, all of a sudden, the chain behaves exactly a Gaussian chain or free joined chain. All right, so this is very weird. So if we have one chain, it will expand. But if you feel its neighbor, if it's built like in a bottle in solid states or in melt, it's actually behave exactly as a random walking Gaussian chain. It's mind-boggling, right? Why? Of course, we never thought about that, and I'll tell everybody the answer. So it needed to be explained at a fundamental level. First is why they would expand. So one of the famous scientists called Dijen, he's a polymer physicist from France, and he won Nobel Prize in polymer physics, probably one of the big shots in the field. He basically predicted in melt states, and he can measure that. So in the melt states, the polymer has actually behaved like freely joined chain. And he kind of said that simply, why in the melt it will be behave? Because in the melt state, one of the signature is you have a lot of chain around it. It's fully packed, right? When we saw in the solid state or in the melt. It's no longer a chain that is far away from another chain. So when it's really dense, you have a lot of winding, and let me pull. Which one I can pull without kill a device? Probably not a good idea. I want to pull the green one, but let me hold this in. So if I have a green one in the black, you can see it and feel it, right? But for this chain, it just cannot tell if it's from myself or it's from another polymer chain once it's fully entangled. So the repulsion from the polymer chain itself versus neighboring chain, because the expansion basically coming from, they have exclusion volume, they want to expand. But if they have another neighbor is occupying the same space, so the force cancel each out. So there's no expansion for the polymer chain. So that would be the very special case in melt states, because the chain can't see if it's surrounded by itself or its neighbor, so the force cancels each other out. So there's no expansion force. That's a simple explanation.
Can you re-explain that?
Sure. Let me explain it properly. Let me pull something. Oh, there is another one, but it's also black. You have a different color one?
Yeah.
Oh, Amy, you saved my day. I love that. Oh, perfect. So if in the melt state, I want to mess up your cable. It's possible. Imagine now we have multiple chains. Imagine this is now the assembly of your polymer. Right? It's highly likely to be a coil, and there's coil if we're on another chain. So now let's look at this segment. This particular one my finger is holding. So it's closer to itself, but it's also closer to a neighboring chain. So they both says, get out of my room, I want more space. It says, go that way. The other guy says, no, go that way. So this chain feels pushing force from both ends, and they happen to be cancel each other out. So there's no net expansion if we don't have this one. It will only have expansion from itself, okay? And that would be one way to observe the freely joined chain is in the melt states, you can have a freely joined chain. In good solvent, it will be expanding. So we all know that there's another condition defined by polymer scientists to be following a 3D joint chain. That is called a theta solvent. And I don't know why the name is so strangely. It's just called theta solvent. So at this solvent conditions, your polymer will again behave like freely joined chain. Okay, so what the heck is this theta solvent? What's so special about this solvent, right? So this solvent is not a good solvent. Good solvent will dissolve it. And we know you can mix different solvent to change solvent quality. Let's say my polystyrene dissolved in toluene, but it didn't dissolve in, let's say, ethanol. So now if I add a little bit of ethanol into my solvents, you can add a little bit, a few drops at a time. So the solvent quality is deteriorating slightly, but it's not so terrible that your polymer chain just collapses and precipitates out. It's not that bad yet. It's still dissolving in there. But you can imagine, we talked about at the very beginning, your polymer coil goes from 30 nanometer-ish for polyethylene of 2800 grams per mole. And if it's fully collapsed, it's just 5 nanometer, right? So going from 25 to 5, we can reduce it such that the size, the solvent is just so, it's slightly bad such that your polymer chain end-to-end distance happen to match a 3D joint chain. Okay? Does that make sense? So the theta solvent is in between good and bad solvents, forces your polymer coil to collapse to be the dimension of a freely joined chain. So those are two special occasions. So it's actually not hard to make this theta solvent. All you need to do is do light scattering. You know the bond length, and you can do light scattering to measure the coil, how big it shrinks. And you can see, for example, when you use toluene, I forgot what exactly, for polystyrene there is solvent and just people by changing the temperature, because temperature also impacts solubility. So you can go from high temperature to low temperature, it will cross this theta solvent, theta temperature, okay? But as long as you know that, although it's so ideal, in most of the case, idealize the chain. Oh, it's okay. Although you know that idealized the chain, it does not exist a lot, but there's a few special cases it exists. So those are melt states, and those are in the theta solvent states. Okay, so let's keep going. So at least I want to cover everything we talked about. So, how do we calculate the random walk if we have some interesting structure, not just a polyethylene, not just the CH2. So let's use this as an example. So what if we use a polybutyl mesacrate? So in this case, it's not hard, because again, we can use the total molecular weight divided by repeating unit molecular weight. But remember, this time, our repeating unit is big. It's a giant molecule. So you need to calculate the right one. And you need to calculate the number of bonds along the backbone. In this case, we need times a factor of 2. Again, this is because there is half bond, 1 bond, half bond. So that's why in this case it matches polyethylene. Okay? But what if we have strange bonds? Again, in random walk, what if we have now a carbon-carbon bond, but also carbon-oxygen bond? If we use polyethylene oxides. Everybody familiar with PEO? So polyethylene oxide will be CH2, oxygen. Yeah, so this would be the oxygen. So you would have, in the bracket, you would have 1 carbon-carbon bond, 1 CO bond, and this would be another half carbon bond. So adding together, each repeating unit should have one carbon-carbon bond, two carbon-oxygen bond. Okay? So in this case, you can again calculate end-to-end distance, but it's a little bit complex because carbon-carbon bond now will have a different length than carbon-oxygen bond. So you do need to apply end-to-end distance slightly modified. So this example, end-to-end distance will be number of CC bond times of length of CC bond square. And you can count number of carbon-oxygen bond and times of number of length of carbon-oxygen bond. So still in the freely joined chain model, you can use that to calculate end-to-end distance square. So this teaches you how then now you can calculate all kind of bonds along backbone, not just counting the carbon-carbon one. And now we finally catch up what we talked about in freely rotation chain. Freely rotation chain, we talked about how does this impact the size of molecular. We talked about when bond angle is fixed, but the phi is random. We can get end-to-end distance for this model. REE square will be equals to, again, self-turn and cross-turn, but in this time the cross-turn is not 0. So we ended up end-to-end distance square equals to NL squared times 1 plus cosine phi, 1 minus cosine phi. And we already go through that last time, right? So this slide we can skip, talks about how bond angle impact the size. Oh, this is example. Now tell you, what if you have multiple bond angle? It happens again if you have not just always carbon, 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 if you have carbon, oxygen, carbon, oxygen. Now it's possible you can have two bond angle, phi 1 and phi 2. Oh, here is the answer. So we can take average of phi 1 and phi 2, use this modified equation. So NL squared is the same, and this will 1 plus cosine phi 1 angle, 1 plus cosine phi 2 angle, and 1 minus cosine 1 times cosine 2. Yeah, question?
What would the L squared be? Well, I guess in that case it would be the same, but in the case
Yeah.
of PEO where you have carbon bonds and then carbon oxygen bonds.
Good
would you
question.
modify that too?
Yeah, I imagine we should, but it's not on the top of my head. I can get back to you on that.
Okay. Yeah.
I believe that should be modified. But this one is assuming bond angle is the same, only is the bond length is the same, only the bond angle is different. Lastly, we chatted a little bit about hindered rotation, but we didn't talk about hindered
Can
rotation.
you go back to the previous slide for a second?
Amy, yes. All right. Everybody had it down, or you can have access to the presentation in the Canvas if you have trouble access that. Let me know. Okay, all good?
Yeah.
All right, I should wrap up in the next few minutes. So this is a restrictive rotation we talked about briefly. So now when the phi is restricted, in addition to in addition to the theta, we entered into some people call it rotation isomeric state, or it's basically the same as hindered rotation state. Okay, so in this case, your theta is fixed, but now again, dihedral angle phi has a fixed number too, because of which direction they want to rotate to. Okay, so this is the first half is exactly the same as freely rotation bond. So you can see influence and bond angle is reflected by this bracketed term, and influence of bond rotation is showed up there. So this would describe the most accurate idealized chain model ever. So if you consider the theta difference, phi difference, you're going to add 2 terms here. Okay? Yeah, Joseph?
Why are the phi cosines averaged and the theta cosines aren't?
Because when the rotation, it's not just a one angle, it's actually distribution. So that's what is, we're considering what is the average of cosine phi. And in the next slides, I'll show you some slides you guys are very familiar with, is which we discuss about. We're pretending we're the bond we're looking at. So when we rotate, it's not going to be one bond, but it will be distribution. So that's where all the potential in phi, we need to take an average and get the value. But we want to go that deep in our exam, so that would be something for you guys to understand, what the influence of phi. But briefly speaking, if you have rotation isomeric state, it will make your chain slightly bigger. Again, it's a restriction, makes your chain hard to rotate into the lowest energy state. I'll give you guys an example. I believe there is one. So this is another example, shows you how to calculate theta, the average. So we need to take energy potential divided by RT. R is our gas constant and T is temperature. So this is a bit complex, so we don't want to cover in exam, but you need to know when we know the rotation energy difference, this can be calculated using a computer, using a density function theory. So it's a tool you can calculate what's the bond rotation potential. You can do that. So once we have that, we can calculate average cosine theta and cosine phi, and we can put in this equation together. I'll show you some example. So this is example, and the only example we're going to show you guys is this says for polystyrene. So we have no conformational energy for trans. Gauge plus, Gauge minus are 4 kilojoule per mole, 0 and 10 respectively. So we can determine the average cosine theta. And okay, so I need to slow down because I don't think everybody familiar with this sign. So what is this sign? Integral. So that is the integral sign. Great. So for those who already know it, that's very good. So for those who don't know, integral means integrate this value within a range, and we typically write the range on the left corner. So this sign, integral sign, we usually write a value. So that means we need integral from 0 degree to 360 degree. And using the phi, integral d, always give a d, is the value of what we need integral with. So that means we're going to integral with d phi. And I know not everybody has studied this, so I'm going to rule out these in the exam as well. But you guys need to know, when you read the symbol, you at least need to know what that means. So when we integrate it, we can get total energy, and we can use the cosine theta of this energy to calculate average bond angle. So this will be an example. We can calculate out the average phi will be 75.2. Okay. Questions? If not, I'll try to wrap up in next slides. So, all right. Yeah, this is a perfect wrap-up slide. Let's see. Yeah, let's wrap up at this one. All right. So, for the freely joined chain model, we know R end-to-end distance equals to NL squared. But for the other two models, it's not. And typically, it's bigger than NL squared. So we can define this characteristic ratio, which defined as what is the actual end-to-end distance of your molecular for all the model is not non-ideal chain. Divide by theoretical end-to-end distance, which is here, we can get this value. So what this is basically expansion factor. So let's look at here. For freely joined chain model, when end-to-end distance it will be always be 1, right? Because freely joined chain, your R squared divided by NL squared will be 1. It's always 1. For freely rotation chain, you could have, depending on the bond angle, you can have Cn bigger than 1. So this is an example where we showed you, for freely rotation chain, when we fix the theta, C infinity will be exactly 1. I forgot if 1 plus or 1 minus. Let's use 1 plus cosine theta. Cosine phi. Then 1 minus cosine phi. Okay. This value will be bigger than 1. That's why your chain will expand. And if you have independent hindered rotation, your chain will expand further. So this example shows you how big the expansion will be. So when we restrict the bond angle and bond rotation angle, your polymer coil at a bigger number of bonds, let's say 100 bonds, it will saturate, and you will see those two cases all will be bigger than freely joined chain. All right, with that, I'm gonna stop. Any questions? Comments?
Yeah.
Yes.
Last course you said the expand or shrink of the chain of
Yeah.
freely rotation chain
Right.
to the bond angle.
Yes, that's true.
Yeah, bigger than 90 degrees. It's expand.
Right. It's again, most of the polymer will have bond bigger than 90.
Okay.
So for example, sp3, like polyethylene, it will be 109.
Okay.
If you have a double bond along the backbone, the bond angle will be 120. If you have a triple bond, the bond angle will be 180. So theoretically you can have a negative bond, but it will be very complex molecule. For all the polyolefins, it will be bigger than 90-degree angle. Okay, if not, then I'll try go back and take a look at last year homework I'll assign. And one thing I heard from Dr. Ma is she don't grade the homework. I think that's a great idea. I'll give you guys the homework. I'll give you guys the answer to the homework a week after that. You guys can take a look. Then we can discuss in the classroom about homework if you guys have a question. I'll start assigning that. I'll give you guys the accurate number, and I'll take a picture of what the textbook 3, and just go to the Canvas. The homework number need to match what I posted there. If you have a textbook 2, you might have a different problem set, okay? So just make sure, look at that. Does it sound good?
When will that be due?
No, there's no due date.
Oh, no due date.
Right, I'll give you the homework. I'll give you the answer a week from now. But I think the other thing I heard from the professor yesterday, I really enjoyed her dinner with her. She said they usually have a study group. Do you guys want to have study group? Like you guys can study together?
I mean, we kind of already do, but yeah.
Okay, great. We should do that. You guys should meet maybe once for every 30 minutes, once per week. That will be a good way. And I can reward you guys for forming a study group. Just let me know how you guys want to be rewarded. I'm open to that. Okay, with that, I'll finish. Then I'll talk to you guys again next Tuesday.